In this highlight video, we're going to turn things around and we're going to talk about the oxidation of carbon-carbon pi bonds. After watching this video, you should be able to categorize different methods to oxidize alkenes, including predicting their products and reaction mechanisms. And you should be able to describe the oxidative cleavage of alkynes as well. Here's a preview of the reactions we're going to look at in this video. The first reaction converts an alkene to an epoxide. So this is called an epoxidation reaction. We've already seen the reactions of epoxides, and in fact we've seen one reaction that converts an epoxide to a 1,2-diol. We're going to see a new reaction to convert an alkene to a 1,2-diol, though, and this is called a dihydroxylation reaction. The final reaction of alkenes is called an oxidative cleavage. And it cleaves the entire carbon-carbon bond, both bonds of the double bond, to form two new carbonyl compounds. And this specific reaction is called an ozonolysis, because we use ozone to do the cleavage. Notice as we go downward in this list, we are getting more oxidized. The last reaction that we'll look at is the oxidative cleavage of an alkyne. And because there's two pi bonds, it oxidizes one step further, and this gives a mixture of carboxylic acids. This as well is an oxidative cleavage. Also will be an ozonolysis. We've already talked about the reactivity of epoxides, but they don't do us much good in synthesis unless we know how to make them. So the main way to make epoxides is to oxidize alkenes. So we're going to have the reaction of an alkene and a peroxy acid. All right, so this is like a carboxylic acid, but it has one additional oxygen in it. This reaction delivers one of the oxygens of that peroxy acid. In fact, it delivers this oxygen right here to give us an epoxide plus the carboxylic acid. Right? So the alkene gets oxidized and the peroxy acid gets reduced. Let's take a look at how this works. I think this is kind of a cool reaction. I'm going to draw this peroxy acid in a certain way that helps us draw the mechanism. So it kind of links back around in a circle like this. And what we're also going to do is we're going to compare this reaction to a reaction we've already learned about, and that's the first step of the bromination reaction. So remember, in the bromination reaction, the first step is the nucleophile, the alkene is the nucleophile reacting with the bromine as the electrophile. So the pi bond reacts with bromine, and bromide is lost. A similar step takes place in the epoxidation. So the pi bond attacks this oxygen here, and the rest of this molecule comes off. The second part of the bromination is the non-bonding electrons on this bromine link back up with the carbon. And what did this give us? Remember, this gives us the bromonium ion, okay, plus bromide. All right, so a similar thing happens in the epoxidation reaction. There's a Couple more arrows though. So this carbon here can't really accept the electrons as I've shown it because that carbon already has an octet around it. So what happens is the pi bond goes up here and grabs that proton. And because it pulls off that proton, it frees up the electrons in the oxygen-hydrogen bond. And those electrons go back down to connect to the carbon. When this happens, the oxygen gets linked up to the pi bond to the carbons. And let's follow our arrows. Look at from this oxygen down here, I now have a pi bond here. Oxygen here connected to the hydrogen. And here's our group over here. So we've generated this epoxide and our carboxylic acid. Pretty cool, huh? Let's look at a couple of examples. So we're going to look at two epoxidation reactions. The first one starting with this cis-butene, right? So this is going to, no, this is trans, and this is the cis, right? So let's look at the epoxidation of these two reactions. So the oxygen for the trans can be delivered from either the top of the pi bond or the bottom. That's going to give us two possible products. I'm going to draw this kind of from the side angle. So looking straight onto the epoxide, the methyl group is going to be going out towards us with an H going back, right? Because there's an H here and an H here. On the other side, the methyl group is going to be going back and the H is coming forward. So this is a syn addition, and if we start with trans, we're going to get an epoxide ring that's also trans, that tells us that the two methyl groups here and here are on opposite sides of the ring. Now the second possibility is going to be with the epoxide oxygen going down. Likewise here though, this methyl group is still going to be coming forward. The H is going back. Over here, the methyl group is going back and the H is coming forward. So again, this has one methyl group front, one in the back, so this is also trans. So if we start with trans, we get trans. What about the cis? Same rules take place. The oxygen can come from the top or the bottom, so we can draw these the same. But in this case, we started with cis, and our product is going to be cis. We can draw the other product, this, but likewise, we started with cis, we get the cis product. All right, so let's compare these pairs of products. So what's the relationship between these two? Could they be superimposed? No, these are enantiomers, right? Non-superimposable mirror images. What about these two? These two are the same because there is a plane of symmetry right through the middle here, and so this molecule is meso. Right? So we have three possible stereoisomers. Both of these reactions are stereoselective. right? Because if we start with the trans, we only get 2 out of the 3 possible stereoisomer products. If we start with the cis, we get only 1 out of the 3 stereoisomer products. So it's selecting for some subset of the possible stereoisomers. But there's another thing that's going on here as well, and this is called stereospecific. Okay, and this is where we're comparing 2 reactions of different stereoisomer reactants. So when 2 stereoisomers as reactants react differently. In this case, what they're doing is they're giving us different products. Trans gives us this pair of enantiomers that are trans, and cis gives us the meso-cis compound. So the stereoisomers that are reactants react differently to give different products. Other ways that reactions can be stereospecific is that perhaps one stereoisomer might react, the other stereoisomer doesn't react. And this happens a lot in biology when we have 2 reactants that are enantiomers of one another. They react with an enzyme in the body or in a living system, and that enzyme only recognizes one of the 2 enantiomers. So one enantiomer will react, the other enantiomer doesn't react. And so that would also be a stereospecific reaction. Like I mentioned, we've already seen a way to make this, call this a vicinal diol. Right? Remember, vicinal means that we have 2 functional groups on adjacent carbons. And this, in fact, is a trans vicinal diol. So how do we make that? We can make it now because we know how to do an epoxidation reaction. We can react the alkene with a peroxy acid. Don't worry about what this R group is. There's a bunch of different ones you can use. This gives us the epoxide, and the epoxide would be either on the top of the ring or the bottom. In fact, those are both the same compound in this case, right? And then we can open up that epoxide either with hydroxide, or we can use water and acid. Remember, the nucleophile comes from the side opposite of the epoxide oxygen to give us this trans product. Okay, so from the alkene to the diol, this is a net anti-addition. What if we wanted the syn addition? What if we wanted the cis vicinal diol? Well, then this is just our lucky day. We have 2 ways to make the cis vicinal diol. First way is to use potassium permanganate. Here is a common oxidizing agent. And notice that these conditions are in the presence of hydroxide, so these are under basic conditions. The other method, which gives us the same type of product, uses this osmium. It's called osmium tetroxide. And it uses sodium bisulfate, which is under acidic conditions. So we choose one or the other of these if our substrate molecule was sensitive to either acid or base. Otherwise, we could choose one or the other. Both of these reactions include a concerted syn addition. Okay, so this step, look at this, is concerted on both cases, where the pi bond, this looks a little bit like that epoxidation, doesn't it? The pi bond reacts with the oxygen. The other oxygen comes in, and it has this syn addition, so it has this ring with the metal in it, but notice that both oxygens are on the same side. This has the manganese in the ring. This one has the osmium in the ring. The second part of this is simply what we would call a hydrolysis. Okay, hydro means water, lysis means to cleave. So we're cleaving this ring, cleaving these bonds, this one here and this one here, or this one here and this one here, with water. Okay, the H's are going to go to the two oxygens part of the ring to give us these two alcohol oxygens, and the hydrogens would go to the metal, or the oxygens on the metal. All right, so in both of these cases, we've done a syn dihydroxylation because we've generated this cis vicinal diol. So we have two ways to make diols. We can either epoxidize and open the epoxide with water or hydroxide to get the trans 1,2-diol, or we can do the direct syn dihydroxylation with either potassium permanganate or osmium tetroxide. We can even oxidize an alkene one step farther. So this is going to be the oxidative cleavage reaction. So we're not only going to oxidize both carbons, but we're going to cut the double bond into two. This is called the ozonolysis reaction. So let's just show how we work out what the product is first, or the products. First thing we're going to do is we're going to cut that double bond right in half. And I'm going to add this other H so we can keep track of it. So I'm just going to draw these two pieces out like this, and I'm going to just draw half of the double bond. Okay, and here's my other side and half of the double bond. So all I did was cut the double bond and leave half on each side. To draw our products, all I need to do is add an oxygen to each of those double bonds. And so we're generating these two carbonyls. Notice that when there was a hydrogen on that end of the double bond, we generate an aldehyde. When we have two carbons on the end of the double bond, we generate a ketone. So that's easy enough, right? So let's see how this actually works. This is kind of a cool reaction as well. But maybe I think about that as all these reactions. All right, so let's draw this out. So here's our alkene. It's going to react with ozone. So let's remind ourselves of the structure, of the Lewis structure of ozone. Okay, so ozone has 3 oxygens. How many valence electrons would that have? So we have 3 oxygens, 3 times 6. We have 18 valence electrons we have to take care of. All right. Ozone has the 3 oxygens linked to each other like this. That uses up 4 electrons, 4, 6, 8, 10, 12, 14, 16. Where can I put the last pair to have all of the oxygens have a full octet? Well, the one place I can put it is right here. All right. So now we know already that oxygen, if it has only a single bond and 3 pairs of non-bonding electrons, has a minus charge. And when an oxygen has 3 bonds to it and 1 non-bonding pair, it has a plus charge. All right, so ozone has this interesting structure where it has both it's overall neutral, but it has a plus and a minus. So this reacts with the double bond. All right, the way we can draw this mechanism is this can draw to one side of the alkene, This comes off to react with the other end of ozone, and these electrons can be drawn back to the plus. What do we get when we do that? Okay, so we have our methyl and our H. We have an oxygen, 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 and here's these other two methyl groups. All right, so it's overall neutral at this point. This is called the mole ozonide. I don't know why. I didn't make it up. All right, so this goes through some really interesting step here, and the book doesn't actually show us this, but I think it's cool, so I'm going to show you. So the next step here is for one of these oxygens, we could draw it either way, to go down and form a double bond here, and we're going to cleave the carbon-carbon bond. It's going to go there, and this is going to go onto that oxygen. So if we follow our arrows, we have formed a pi bond here, and a pi bond here. And this is going to have a plus, and this is going to have a minus. Okay, now the amazing part of this reaction is that these two pieces break apart and then they recombine. All right, so we're going to rotate this molecule around. And I'm going to draw the same two structures, but they're going to be facing, the one on the right is going to be facing the other direction. This, so plus and minus. Now they recombine. So this can go to the carbon, this can go to here, and this goes towards the plus again. This forms a new ring that now has two oxygens on one side and the other oxygen on the other side. This is called the ozonide. From here, we do the second step of the reaction, and this is sometimes called the workup. What it's going to do is it's going to destroy this ozonide, and it's going to destroy any excess ozone that we have in the reaction. In fact, this is actually a reduction step. So it's going to reduce the ozonide and get rid of one of those three oxygens. So we can use either zinc and water or dimethyl sulfide, which is pretty smelly stuff. All right, so what we end up with then is we remove one oxygen and we end up with our two carbonyl groups. And the zinc or the sulfur, the dimethyl sulfide, pull off the extra oxygen. Let's look at a couple of examples so we can predict the products. All right, predicting the products, like I showed you before, is pretty easy for the ozonolysis reaction. So all we do is we look for the double bond, we cleave it in half, we can redraw the two pieces with a double bond. We got one there and one here. Remember, on this end of this has two hydrogens. So this would have two hydrogens over here. And then all we have to do is attach an oxygen to each side. Right? So in this case, we get a ketone. And this is aldehyde. This is called formaldehyde. Right? This is the smallest of the aldehydes. We can even do an ozonolysis of an alkene in a ring. We do just the same thing. We're going to cleave this bond. Let's redraw it. I'm just going to leave a little extra room in here now. Here's an H because we had an H here. All we do is add an oxygen and an oxygen. Right? So we've opened up the ring, and we now have, so this would be like this. 6, 7 it should be, right? And this. So we get a ketone and an aldehyde. We can even do an ozonolysis on a molecule that has more than one pi bond, or more than one alkene. We do it the same. It cleaves here, and it's going to cleave on this side. We're going to just open up each of those, add an oxygen, and formaldehyde on the end, like this. So we get these 3 products. Like I showed you on the preview slide, alkynes can also be oxidized. So it's going to cleave this entire triple bond, and because there's 3 bonds to oxidize, each end is going to be oxidized one more step than it was with just an alkene. So what we end up with is a carboxylic acid on one end, so on this end, and the other end doesn't have any, just has an H on it. So it could, I guess we could predict that it would go to here. This is formic acid. But in fact, that goes farther and gets oxidized all the way to carbon dioxide. All right, so if we have an internal alkyne, we get 2 carboxylic acids. If we have a terminal alkyne, we get 1 carboxylic acid and carbon dioxide. So we've really added up to a lot of reactions now, and we can really start to do more chemical synthesis.